Okay, yeah, we're on Hess's Law. So, Hess's Law, you guys, is not something new. I've seen it at ordinary. That's advanced level. So, let me give you the advanced definition. Hess's Law states that the enthalpy change that accompany a chemical reaction is independent of the root technique, provided the initial and the final condition are kept constant. What's the physical significance of that? It means that starting with a particular reactor, no matter the path you are taking, you are going to have a final product. Consider these two reactions above. Second hand. N2 plus O2 the N2 NO2. The equation is not balanced. As a balance the equation. Balance the equation out the two. So two of those. So the main aim of the reaction is the synthesis of nitrogen dioxide. This is the final product, MH. I can synthesize the nitrogen dioxide passing in another way or another path. Consider the second reaction. Add NO plus O2 be NO2. So I can see everybody here. Add two reactions on the board, A and B. Reaction A with B. Reaction A and B are different but similar. Different in which sense the reactant are the same. We have N2 plus 2O2 giving NO2. The second reaction is NO plus O2 giving NH. So here the even the reaction number is after 2 years to balance the equation. So I need to option. So the equation is balanced. So the main aim of this reaction is synthesis of nitrogen dioxide. But different reactions, the reactants are different. The second reaction, the reaction are different. That's why cases like them we care less of how you manage to have the product. Even if you are started from which product, any type of product or any type of reactant, our problem is to have a final product. The reaction can occur in two steps. In one step, even in 110 steps, if you succeed to have the final product, the enthalpy change accompanied to reaction are the same. But we have a condition, provided the initial and the final condition are kept constant. Condition like what? Temperature and pressure. What two main factors that affect this reaction? Either the temperature or the pressure. Once the temperature change, I doubt if the enthalpy changes will be the same. If the pressure change, the enthalpy change will not more be the same. So that's what his does is stipulating. So before we enter in his law as a core, there are some terminologies that I have to understand. The first terminology is the enthalpy of formation. So let's see some chemical. Enthalpy of formation. Enthalpy of formation. I like in chemistry. Chemistry is ring. That means chemistry goes with balance equation. So there's nothing chemistry can do is alright the balance equation. So let me give you a balance equation. So I have sodium, sodium plus have a chlorine. Yes. Real. Very good. This enthalpy change we call it something called cells. This enthalpy change we call it delta H of formation. What's the enthalpy of formation parallel? This is the enthalpy change when reactants in a normal physical state react together or combine together to give an ionic product under standard condition of temperature and pressure. When they say they react in a normal physical state, sodium is a gluon element, so sodium is an alkali metal. The physical state is solid. Chlorine is a gas, it's a non-metal. Chlorine is the key. The physical state is it has. So one sodium solid that combine with chlorine gas to give sodium chloride substance. The name given is enthalpy change is enthalpy of formation. So the enthalpy of formation, this is the enthalpy change when an ionic crystal is formed from the constituent gaseous. Is formed from the constituent element in their normal physical state under standard condition of temperature and pressure. On the bottom of the enthalpy of formation. We can also have the lattice energy. So lattice energy, so you this is answer the lattice energy. The lattice energy is quite different from enthalpy of formation. But see what with lattice energy. I still have the sodium gas plus chloride minus gas giving sodium chloride. So in this case, I have found sodium chloride solid, sodium chloride solid. The two are solid crystals or solid chloride are the same. But here I combine my sodium solid plus chlorine gas to give sodium chloride solid. But here I combine my sodium gas gaseous plus chlorine minus gas to give sodium chloride. What the difference between the enthalpy of formation and the lattice energy? I've already defined the enthalpy of formation. The lattice energy is simply the enthalpy change when an ionic compound is formed from a constant gaseous ions under standard condition, temperature and pressure. Another condition is the temperature should be like 0 degrees and the pressure should be 1 degrees. So this is the enthalpy of formation, the enthalpy, the lattice energy. So now I'm going to see enthalpy of atomization. The enthalpy of atomization. The enthalpy of atomization. I can have sodium solids giving solid gas. Yeah, atomized means I'm starting from an element in gaseous state. I'm going to the gaseous atom. So in this case, I'm moving from sodium solid to sodium gas. In this case, change its state from the solid state to gaseous state. In this case, at the ordinary level, we say that it has undergone a sublimation. But here is the enthalpy of atomization. That means I atomize sodium is now in a gaseous state. It's not only metals that we can atomize. It's not only solid that we can atomize. We can also atomize gases. So atomization, we're actually breaking. If it's a metal, we're breaking the metallic bond. If it's a covalent compound, we're breaking the covalent bonds. So consider a molecule, a chlorine molecule or a halogen. In halogen, we're having half a chlorine. That's giving chlorine back. Half chlorine, you guys should like see since when there's a fraction in elements or so is it really possible to use fractions? It's very possible to use fractions. The chlorine molecule will have two. So the next thing we got, if you can see clearly, is Hess's Law. So what does this law say? So this is the state that the enthalpy change that accompany chemical reaction is independent of the weight packing, provided the initial and final condition are constant. So consider these two reactions, but I can have two reactions. So let me give you the reaction. So the reaction are N2 plus O2 giving NO2. I put two here to balance the equation. But the equation is not yet balanced. I check the number of oxygen. So having 2 times here, that's 4O. The other side I have O2. So I multiply the number of oxygen by 2. So multiply the number of oxygen by 2. I have 2 times 2, which is 4O. 2 times O2, that is 4O. The equation is balanced. In this case, I have reaction 1. So reaction 1, I can call it reaction 1. So see reaction 2. Reaction 2, I'm still deciding O2, but I'm taking different reactants. The reactants in this case are I have NO plus O2. It means NO2. One more the reaction minus. So I put 2 here to bind to equation. I call it equation 1 and 2 are same but similar. In fact, they are similar, let's see. Similar in which sense? The products are the same, but the reactants are different. For the first reaction, I have N2 plus O2 giving 2N2. Reaction 2, I have NO plus O2 giving 2NO2. In a nutshell, that's why Hess's law is telling us. Hess's law tells us the enthalpy changes for reaction 1 and reaction 2 are the same, even though they don't have the same reactants. So the enthalpy change that accompany a chemical reaction is independent of the route taken, provided the initial and final conditions are kept constant. The conditions in this case are what? Temperature, pressure. So those are the two factors that might influence the enthalpy change of chemical reaction. Remember that the enthalpy change is a heat change accompanying a chemical reaction. So reaction A will have reaction 1, reaction 2. Okay, that's his law. So before now we go in the curve of Hess's law, we have some application of his. The application of Hess's law involve 1. It's the relation of the enthalpy of formation from combustion data. So that's the first application of Hess's law. That's what we're studying. Let's go to how we can apply Hess's law to then the enthalpy of formation of a compound from combustion data. So how is money donation? Or let's not like application of Hess's law. Application of Hess's law. Application of Hess's law. Why? It's the relation of the enthalpy. It's the relation of the enthalpy of formation from combustion data. The combustion data will be given to you, but you have to draw the Hess diagram. That was obvious. So just talking like this, that is big. Huh? So I have to have an example. I have to take an example. Using that example, I will teach you how you will be able to have the answer. How to determine the enthalpy of formation of a compound from a particular or from combustion data. So example. So I now give 2 examples for better understanding. In example 1, here example 2. So example 1 is quite obvious. Example 2 is a bit complex, that not impossible to solve. So example 1. Pipe mix. Calculate the enthalpy. Need the enthalpy of formation of methane in that the enthalpy of combustion. These are the enthalpy of combustion of carbon. Hydrogen, and methane are minus 416 footage of 1 command minus 286 curie in 1 and minus 1.21 kilojoule. So those are the enthalpy of combustion that's given to you. So let me give you a basic. Calculate the enthalpy of formation of methane, given that the enthalpy of combustion, carbon, highly, and methane are negative 460 kilojoule per mole, minus 286 kilojoule per mole, and minus 1121 kilojoule per mole. So I have to take the data here because whenever they give you a question, you have to take the data. So taking the data, now in the enthalpy of combustion of carbon, enthalpy of combustion shower, very sorry, enthalpy of combustion of very 9,286 Enthalpy of bubble of methane minus 1,200, 1,181. So those are the enthalpy formulas. Then remember, methane is formed from the constituent element which has carbon and hydrogen. So the constant element is kids. So our big board so that I can easily do the correction of the example. So calculate the enthalpy information on methane given that enthalpy of the motion of carbon, hydrogen, and methane are minus 116, minus 286, and negative 1,121 kilojoule in both. So let me start by writing the balance equation. The balance equation. So the balance equation here is methane is carbon plus hydrogen, being solution. The equation number. So I have to balance the equation. The number of carbon atom on the left and the right are the same. So here, as carbon on this side, I have carbon on the other side. But hydrogen is unbalanced. The balance side is in equity here of H. So that 2 times 2 is 4H. Starting 4H. The equation is the true balance. So I'll call this letter H of. Look at this. But remember that the enthalpy of formation has been given to us. So if you burn carbon, you have carbon dioxide. You burn hydrogen, you have water. For burning of carbon, and CH. You burn hydrogen, water. When you burn methane, now CH. So I put the data Edward. And one before the coefficient of carbon is 1. That's why I'm multiplying by 1. The coefficient of hydrogen is 2. That's why I'm multiplying by 2. So the coefficient of hydrogen is 2. So it will be 2 times delta H2. Delta H2. So how we get the H1, 2 delta H2, delta H2 in that formation. So I have to make the H of formation subject to the formula. So I go in the clockwise direction, that is when you loop. Apparently loop, I have the H of formation, delta ST, delta M or delta H2. Let's see how we can solve this exercise. I have delta L of formation, so delta L of formation plus delta H3. So all those guys that are going in clockwise direction are positive. Those arrows go in the opposite direction are negative. The negative arrows there are delta H block, 2 delta H2, because they are going in this direction. Delta H3, delta H3 and delta H formation are going in the positive direction. So delta H formation equals to delta H1 plus 2 delta H2. I make delta H3 or delta H formation, something the formula. So delta H formation. Delta H1 plus 2 delta H2 minus delta S3. So what do you place this here? So there's a information over K. I have the H1. So the H1 is relative carbon. So I'm minus the direct. Minus 16 plus 2 into minus 286 minus in bracket minus 1,101 because so in there we get the box to punch. The punch bracket of the minus 416 bracket equals plus 2 times bracket of it minus 286 equals plus bracket 1121 plus 182. So you guys be on the screen, you have to punch and compare the answer. Mine. So that's the answer about to have plus 138 kilo. So this is a very simple exercise. I get a hydrocarbon. A hydrocarbon is a compound made up of carbon and hydrogen only. So now already give you an alcohol. And alcohol is made of carbon, hydrogen, and oxygen. So let's see example 2. So example before we go to example 2, I hope example 1 is quite clear on the board. So the first step is write the balance equation. The balance equation is carbon with the stored energy given methane. I call that data in information. When you burn carbon, we have carbon minus that. Burn hydrogen, we have water. We make use of the stoichiometric coefficient. That means for carbon is 1. That's why 1 times delta F, but C delta H1. For hydrogen is 2. That is 2 times delta H2, which is 2 delta H2. Delta H of formula delta H3. But I use this when I go in positive direction and the clockwise direction, so that delta H information plus delta H3 equals to delta H1 plus delta H2. I make delta N information so that the formula. So let's now go to example 2. Example 2. Calculate the enthalpy of formula of ethanol using the enthalpy of combustion of carbon, comma, ready, and oxygen and ethanol are minus 416, 286 and minus 130 decimal order and kilojoule per mole. So let me read the question. Calculate the enthalpy of formation. Calculate the enthalpy of formation. And now, given that the enthalpy of combustion of carbon, hydrogen, and ethanol are minus 116 kilojoule per mole, minus 286 kilojoule per mole, and minus 1821 kilojoule per mole. I told you earlier that okay, ethanol is made up of carbon, hydrogen, and oxygen. If you see on the board, I like me the enthalpy change of combustion of oxygen. So no more, they need not to give it to you because enthalpy, you cannot burn oxygen. So it doesn't make sense. Burning or combustion take place in the phase of oxygen. Remember step 1. Step 1, you should write the balance equation. So in the balance equation here is the formation of ethanol. But before you even write this, you need the formula of ethanol. So that's where problem starts. Formula of ethanol. So let's take down the data. The enthalpy of conversion of carbon is minus 40. There's the idea of conversion of hydrogen because minus 286. The idea of conversion of C2H6O equals to minus Y321. Those are the data. Now I can want the bot. So what will the bot? Can now solve the exercise. So solving the exercise, now let's solve the exercise. Or the example. Remember that ethanol is made up of carbon, hydrogen, and oxygen. So let's write the balance equation. Carbon is C, hydrogen A, remember that hydrogen is diatomic. Just like hydrogen is, so hydrogen is diatomic. So I mean hydrogen
oxygen. All of these guys combine to yield ethanol to CT A6. So I call it the A for many. But when you burn carbons, they have carbon lengths. I call it as an S1. When you burn hydrogen, you have Madiba. I call it the S2.
Maniba is water. Water in the Douala language. That is Matipa.
So, if you question is balance, so you put 2 here, put 3. Now, oxygen. I multiply the enthalpy changes by the stoichiometric equation. So multiply them by the stoichiometric equation. So here's 2, here's 3, and now there is 3. Once more, I apply physics.
Okay, today do you know what I'm saying? We are doing Kirchhoff law, current electricity.
But here we're not interested in the current electricity. We're interested in how we can use notion the physics to solve any problem. But even though the notion is quite obvious, so here we're going forward direction.
The correct direction means the enthalpy changes are positive. Positive means the direction of formation, the direction 3. So the direction 3, the direction of formation are positive enthalpy changes. So the other side of the equation will let be what the H1, the H2, which are being multiplied by their respectives. You could make a prediction. So if I apply this, I'm going to know the direction of formation plus the direct 3 equals 3. So the direct 1 plus 3 the direct 2. I make the direction from here. Sorry, from here. So the direction of formation equals 2 the H1 plus 3 the H2 minus the H3. Because I'm making the direct formation, survey the terminal. So when this guy, the positive is positive, cross the last and become minus. So the direct formation equals 2.
So the direct 1 plus 3 the H2 minus the H3. Wow. So let me substitute the value. The direct formation equals. So let's substitute that. So it's 2 into minus plus plus 3 h2 minus 2 86 plus negative 1 3 2 0. That's the enthalpy formula. There will be punch it. So what to punch?
So you cannot just stop there, draw the final answer. So you punch it. The punching we're gonna have 2 into minus on the x plus weak engine where's 2 it plus nothing 1 David is equal kilojoule carbon and minus is equal kilojoule for not. So the air of a not people because minus get 3 kilojoule low minus 2. So that's the enthalpy of formation as ethanol.
So I've seen example 1, example 2. So at this moment, at this level, you should be able to determine the enthalpy of formation from combustion data. So we have seen how to calculate the enthalpy of formation of methane from the combustion data. Now I see how to calculate the enthalpy of formation of ethanol still from the combustion data. Now we've seen how to calculate the enthalpy of formation, but for multiple data. For multiple data.